SwayamPrabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. We have been looking at the physical meaning of individual terms in the equations of motion, and we have done two equations, okay, the phi and theta equation in the spherical case. What is left is the transverse or alpha 3 equation of motion. And how do the terms look like? The terms look like del alpha 1 q13 a2 plus del alpha 2 q23 a1 minus a1 a2 n11 by r1 plus n22 by r2 plus the usual terms a1 a2 q3 is equal to the inertia term a1 a2 rho hu3 double dot. So the first term for us looks like del term 1 looks like del phi of q times phi 3 r sin phi. That is the first term. Now, if I again draw the axis of revolution, this is my differential element. Phi direction d phi, okay, and q phi 3 is on the phi face in the 3 direction. Negative phase, it's downward, it will go through the center, and here it is incremented. This also should go through the center. So this is q phi 3, this is q phi 3 plus del q phi 3 del phi d phi. Okay. Now these are still force resultants, so we have to make them a force. So let us begin. On the negative side I have minus q phi 3 r sin phi d theta. Now the incremented side q phi 3 plus del q phi 3 by del phi d phi, and the length also incremented, sine of phi plus d phi d theta. Okay, So this, if we open it out, r sine phi cos d phi plus cos phi sine d phi into d theta. Okay. So if we sum it up, as usual I'll ignore this product because it has 3 differentials. So what we end up is this term cancels with that term. Okay. Then I have q phi 3 r cos phi d phi d theta plus del of q phi 3 by del phi r sine phi d phi d theta. So this last product I am ignoring, this product of this term and the differential, because it has 3 small terms. So now this can be written as del by del phi q phi 3 r sine phi into d phi d theta, which is what we have. The second term, okay, term 2. Term 2 looks like term 2. Term 2 looks like del theta q theta 3 into r. Let us again draw the picture. So this is my element. This is my phi d phi, then q theta 3 is in the downward direction here, q theta 3, and then q theta 3 is augmented del q theta 3 by del theta d theta. Okay. Now again this distance is approximately, if we draw, r sine phi d theta. Okay, we have done this before, so now this angle is sine phi d theta by 2, and so is this angle, and my q theta 3 on this side is going downwards, on this side goes upwards. Okay, and I am looking for the vertical component. Okay, and this angle, the cosine of this angle. Okay, and this angle is a small angle, sine phi d theta by 2. Okay, sine phi d theta by 2, it's a small angle. I am doing the cosine of that angle, so it is actually 1. Okay, so now the components here will be negative and here will be positive. So if this is q theta 3, then I multiply by this distance to make it a full force r d phi. It will come with a minus. Then this side also I need to multiply by r d phi. It comes with a plus plus q theta 3 plus del q theta 3 by del theta d theta into r d phi, okay, and cosine of the small angle, so it's 1 both places, okay. So as a result this fellow goes away, and then I am left with del q theta 3 by del theta r d theta d phi. Term 3. Term 3 looks like n phi phi with a minus sign, r square sine phi n phi phi by r, or minus r sine phi n phi phi. This is my element. Phi d phi, okay, and n phi phi. N phi phi is in the negative direction here. Here it's in the positive direction. So n phi phi plus del n phi phi by del phi d phi. Okay. So now these are force resultants. So if we want to make a full force out of them, we get, we look at this curved element. I have this curved element over here. So my n phi phi negative side, n phi phi plus del n phi phi by del phi d phi okay. So now we will have to make it a full force. So minus, okay, so we are going, this angle is d phi, this total angle is d phi. If I break it up, I get these two forces. If I break it up, I get these two forces, okay. And I am looking at addition in the third direction, so the forces, both of them will add up, both the forces will add up, but with in the negative direction. So I have n phi phi multiplied by r sine theta d phi, okay, that's for this side, and this side is augmented, but I will right away say that this is a smaller term than this, so I am going to ignore it right here, okay. So I get a doubling plus further what do I have, if this is my d phi by 2, this is d phi by 2, that is d phi by 2, then this component is the sine component, so into d phi by 2, okay. So let me do this. N phi phi r sine phi d theta into d phi by 2 is this component. Similarly that component, so it gets multiplied by 2. So we get n phi phi r sin phi d theta d phi with a negative sign. That's what we have. Okay. Next, the next term is again a negative term. Okay, n theta theta. Let me write it in red. N theta theta by r into r square sin phi, which is equal to n theta theta r sin phi. Okay. So if I look at this, my axis of revolution, the element phi d phi, okay, and n theta theta. So I have n theta theta coming here, n theta theta coming there. Okay, and this length. This is n theta theta plus del n theta theta by del theta d theta. And this last time we saw is approximately r sin phi d theta. And these two forces, this line element, are in a single plane where it goes through the center. It's like a pie. Okay, so if I draw it in the plane, they will look like this. Okay, so this is n theta theta. This length is r sin phi d theta approximately. Now this is the center and this is the radius. This is the radius and this is the incremented resultant n theta theta plus del n theta theta del theta d theta. Okay, so they can be made force by multiplying by r d phi. This length is r d phi. So multiply by r d phi. Okay. Now we are looking for the vertical components. So if I break it up further, the horizontal is a vertical component. The horizontal is a vertical component. Okay. So I need this angle. If this is r sin phi d theta, then this angle is r sin phi d theta by the radius, which is sin phi d theta, and half angle is sin phi d theta by 2. So this half angle is sin phi d theta by 2, and therefore this is the same angle, and therefore this is the same angle, and I want then the sine component. So just multiply by this. So I have n theta theta, convert to r d phi, a force, into sine phi d theta by 2, and the same thing comes from here. and this is a lower order term, we ignore it, so multiply by 2, so we get n theta theta r sin phi d theta d phi in the negative direction. Okay, so that so that settles the third equation of motion. What are left are the external forces, and the inertial term. Okay. Now, so that completes the thought process involved in looking at individual terms with respect to a spherical coordinate system. Okay. So, I hope you can figure out for all other coordinate systems the idea is very similar. Okay. Now, before I proceed to the next topic, there are a few things I'd like to talk about, and those are here. There are some topics I'd like to give a closure to. Now, since we are in the topic of spherical systems, I will continue along those lines. Okay. Now, we have obtained 5 equations. Okay, 5 equations. And of the 5 equations, the first 3 are dynamic equations, and first 3, and the next 2, the last 2 are equilibrium equations, moment equilibrium. Because we ignored the rotational inertia. Okay. And so I didn't interpret them again, we just gave an interpretation of the first 3 equations. Okay. Now, we know that a rigid body in space has 6 degrees of freedom. 6 degrees of freedom. Okay. 3 are translational, 3 rotational. Then how is it that we have only 5 equations? Okay. How is it that we only got 5 equations? So, for one thing, what we did was we have a differential. So, if we plot or if we draw my alpha 1 and alpha 2 axes and the alpha 3, first of all we have a differential element in the alpha 1 direction and we have a differential element in the alpha 2 direction. Okay. Now, we have spoken of rotation about alpha 1 axis using moments like m22. We have looked at rotation about alpha 2 axis using moments like m11. Okay. Now, that is firstly possible because in the alpha 3 direction it is not a differential element. in the alpha 3 direction, it's not a differential element. Okay, it's not looking good, but we have a center line and we have a small but finite thickness, and therefore what did we do? We said the u1 full is small u1 plus alpha 3 beta 1. The big u2 is small u2 plus alpha 3 beta 2. So because of the finiteness in the alpha 3 direction, we could afford a rotation. Okay, there is a middle surface movement and then a rotation about it. Whereas when it comes to u3, we said it moves in unison. The top surface and bottom surface move in u. Okay. As a result of this sort of kinematics, okay, if we balance rotation, now about the alpha 3 direction, okay, because this is a differential element, we will only get an equilibrium equation. Okay. In the alpha 3 direction, we had a finite distance to account for. We had a finite thickness to account for. Whereas here, this is a differential element. There's no finite thickness. Okay. So if we do a rotation about alpha 3 axis, which is missing, okay, we have done rotation about alpha 1 axis and we get moments like m22. If we have done rotation about alpha 2 axis, we get moments like m11. Okay, it's a different matter that we ignored the rotational inertia. It's a different matter, but we have accounted for it. Okay, and that has happened because of the finite thickness. Now if we try rotation about alpha 3, there is only a differential length over here. Okay, so you will get only an equilibrium equation. You will not get a full balance equation, and so it will not appear in the Hamilton's law also. What that means is that u1 and u2 will account for all that is happening to this element in the plane of alpha 1, alpha 2. Separately, you will not get a rotation equation, which you do because of the finite thickness in the alpha 3 direction. Okay. It is not that rotation is not accounted for, it is accounted for in u1 and u2. Okay. So you will not get a separate equation. Okay. So what is that separate equation? If we deliberately try to find out with regard to, let's say, a spherical element now, it will be an identity. Okay, it will be an identity. So time is running out. Okay, so I will stop this lecture here. In the next class, I'll show you how the sixth equation, or the sixth so-called equation, is actually an identity, and therefore will not appear in this set of equations. Okay, so let me stop the lecture here. I'll continue in the next class. Thank you.